Right. So, welcome. Thank you all for being here. Quick note, everything's going to be in English, but I'm sure that you're expecting that, right? Okay, so, well, it's a great honor for us to have here Professor Anderson Rocha from the University of Campinas in Brazil, Sao Paulo, the place that everybody wants to relocate at some point, sooner or later. Anderson he's a director of the Artificial Intelligence Lab and also of Record AI, and he's also director of the institute. He was during the period 2019 and 2023. So Anderson is highly cited. His work is mainly revolving around AI, of course, with applications around social media and forensics. So we were very fortunate to have him here, and we asked him to provide us some indications of his work on the topic of forensics and AI, hoping that will steer some interesting discussions and might even inspire us to go towards that direction or towards that place. All that being said, I think that the floor should be yours now, Anderson. Thank you very much.
So hello, everyone. Good morning, good afternoon. And for those online also, welcome. Thank you for the opportunity to present to you some of the research that we do in the Institute of Computing. Before I start with the research teams, I'm going to give you a quick overview of where we are. So this is Campinas. It's a city in the state of São Paulo, and Unicamp is University of Campinas. And we are right here. There is the Brazilian map, which is like a continent. Here is the state of São Paulo. And in the state of São Paulo, we are the pink one. We are Campinas. So here is Campinas. And the city of Campinas has 2.6 million people, the metro area. Seems big, but when you compare to our neighbor is just São Paulo. So it's 20 million. So compared to São Paulo, we are quite small. So this is the city itself. And it's known as the Brazilian Silicon Valley. Why? It's when you think of this region in Brazil, you have three main vertices. One is Campinas, the other is São Paulo, the city, and the other is São José. São José is the city that makes the plane Embraer. So it's one of the largest plane makers in the world. So São José, São Paulo, and Campinas, these three, each one is 100 kilometers from each other. So in this triangle of distances of 100 kilometers, we have pretty much 45% of Brazilian scientific output and also the industrial production. So this is why the region is called the Brazilian Silicon Valley. And it's there also that we have the University of São Paulo, the University of Campinas, Federal University of São Paulo. So it's several universities in the same place. And my university itself, it has 1,800 faculty, so almost 2,000 professors and 7,000 staff. The University of Campinas has one very particular feature. It is the strongest university in Brazil in terms of partnership with the industry. And as a consequence, or as a cause, here is difficult to say, we are the #1 in terms of patent filings as well. So when you think of a university that's quite aligned with the problems in the industry, the University of Campinas is this university. And it's also the University of Brazil with the #1 ratio of publications per professor. So we are not the university with most professors, but we are with the best ratio of publication per professor. Until some years ago, we had about this number of graduates and undergraduates switched. But now is 17,000 graduate students and 19,000. Before the pandemics, it was the contrary. It was 19,000 graduate students and 17,000 undergrad. So now it keeps changing, but basically it's 50-50. So it's a university with a very big graduate program. Okay. So this is a broad view of the university that I wanted to show you. And one of the reasons that I'm here is to establish partnerships, like to work in common problems, but also to tell you that we are open for visits. If you have, as part of your PhDs, the opportunity to stay like 3 months, 4 months in Brazil, we host students. I was telling Professor Constantinos here that as of September 1st, I'm going to receive a student, for instance, from Rome as part of his PhD, and this is common. I always receive in my lab students from Europe, none to now from Greece, but many from Italy, France, Germany, Sweden, and it's going to be nice if we can establish partnerships in this direction here as well. And on the other side, our students, as part of their PhDs, it's mandatory for them to stay 1 year abroad. So the government, the state government, not the federal one, because in the federal level we have Bolsonaro and that's not a president, okay? So in the state level of São Paulo, we have a policy of more than 25 years already that each PhD student has to stay 1 year abroad, and the state pays for that student to stay 1 year abroad. So we establish partnerships. One of the reasons of the partnerships, it's because we want our students to go abroad and to do research in other centers that we can start collaborations. Okay. So that being said, I'm gonna change gears now to show you some of the research that we do. And I selected here 5 or 6 problems that we have been investigating in my lab. And I call these opportunities in AI and digital forensics because they are very much tied to them. So I'm the director of this lab, Artificial Intelligence Lab. It's called Recode AI. If you have LinkedIn, you can follow us on LinkedIn. We always have talks online, at least 1 per month with researchers all over. So it's also good to connect. So in this lab, we have spread all over the world about 200 researchers collaborating. And in the lab itself, we are 7 professors and about 70 students. It's the number is about 10 students per professor. Okay. So the agenda today is this. Until some years ago, everyone was talking about what's called the 4th Industrial Revolution. So probably you have heard of the Industry 4.0 here, right? But this is like too poor to define the moment that we are living. The moment that we are living today is called the Convergence Revolution. And what is this Convergence Revolution? It's when you have a series of technologies that are accelerating each other. So we have a series of what's called exponential technologies, and each of these technologies is accelerating others. So let me give you some examples. We have pretty much 7 technologies happening today, nowadays, that are exponentials. Here, there are 5, and we have 2 more. So these technologies are biotechnology, represented by the G of genetics, nanotechnology, robotics, Internet of Things, AI, that's 5. And here I don't have quantum computing and blockchain. So quantum computing and blockchain are the 2 others. They are still not that mature, so they are not here yet. But genetics, nanotechnology, robotics, IoT, and AI are the 5 most important. So one example in biotech, you probably have heard of Moderna vaccine, right? So Moderna was a startup before the pandemic. It was a startup of like a few $1 million, but it was a startup. And have you checked the value, the market value of Moderna now after the pandemic? Between the 15 most rich, the richest companies in the world. So it's like valued over $100 billion. So why is that? Because they have a very important technology to edit mRNA. And to edit the RNA, they can solve many problems. One of them was COVID-19. So how Moderna did that? they used AI. So one technology accelerating the other. They had the technology to cut specific pieces of RNA for one purpose, okay? But where do they need to cut? What was the combination of cuts that they needed to do to isolate the spike protein of the SARS-CoV-2 virus? That position was needed to be found. So they needed to find it. And they used the AI in a series of clusters to solve the specific points that they needed to edit. Do you know how many days they did need to create the vaccine? Any idea? We know that 10 months was the time that they created the vaccine to arrive at us in order we could get vaccinated. But how many days did they need to create the vaccine? 17. 17. They created the vaccine of COVID-19 in 17 days. That's something that we never did before. Why? Because they used AI and one very important technology discovered by Jennifer Doudna and Emmanuel Charpentier a few years earlier, around 2010, 2011, and others. That's the addition of RNA. So one technology serving as accelerator of the other. Why I'm saying this? Because all of the things that I'm going to tell you today, it's associated with one of these technologies. So nanotech is the same thing. We have like the decrease of size in many devices that allows us to like sense pretty much everything that we want in the world. Or if we go to an industry, we see robots all around taking care of many of the problems that we have there. Many of the manufacturing is done by these robotics, and everything is connected. So pretty much everything everywhere can send signals, and you can capture those signals and do interesting things with those signals. And this is called the Internet of Things, the IoT. And who processes this and who finds the patterns? AI. So AI is at the center of everything that we are talking about here. And it's another technology that's exponential and accelerating others. And this is what we call the Convergence Revolution. It's not me that I'm saying this. A lot of people, philosophers, they are discussing nowadays that we are living this Convergence Revolution right now with 7 technologies, exponentials, accelerating each other. And in this sense, our definition for AI is the ability of a system to correctly interpret external data. So data from the world, learn from given problems, and use these learned capabilities to achieve specific objectives and tasks through flexible adaptation. Note that there is no philosophy discussed here. We are not talking about, like as Lemoyne said 2 weeks ago, an algorithm that's taking consciousness. We are not talking about that. We are just taking an engineering definition for AI. What is that? Look at the data in the world, capture that data, find the patterns, learn the patterns, store the patterns that you learn, use those learned patterns to take decisions, take the decision, do some action, done. And if you're really a good algorithm, adapt over time, so flexible adaptation. So this is our definition of AI. Basic definition of AI, and it applies pretty much everything that we do. And to complement that, the problems that I'm going to show you, it goes in what we call digital forensics. And if you look at the definition of digital forensics, it's pretty much similar to the definition of AI. So it's the collection of scientific techniques for the acquisition. This is analyze the external data. Preservation, validation, identification, analysis, interpretation, documentation, presentation of digital evidence, normally of a criminal nature. Okay, so this is very associated with AI. And that's why some years ago, I decided to work with developing algorithms in AI with forensics as one of the possible applications. So here's an example. This was a photo that was released some years ago in the elections in the Netherlands. But after some analysis, it was possible to discover that it was a fake. So this is the kind of problem that we want to identify. If a photo is really something real, or if it was modified. Or something like this. This was the Boston Marathon in 2013. And right at the moment of the finish line of the marathon, 2 bombs were exploded. So when you have something like that, and you are able to collect video footage of several of the cameras around, how can you use those images to possibly spot possible suspects? So how could you do that? Or if you have different cameras, could you have, for instance, a virtual actor walking over the streets and combining the different videos to have a longer sequence automatically? So this is something that we wanted to solve. So here is the example of the bombs. There is no sound, but in the original we have. So one bomb there, captured from this camera, then another camera here, several different cameras. So one of the things that we try to do is to combine the different views and have one longer sequence. And at the end, to analyze the clusters and come up with the suspects, in this case, the 2 brothers Czerny. This was published a few years ago, this analysis. So this project, the results of the things that I'm going to present, they are the result of more than 15 years of research. They have given results as publications, patents, and software available. And it's a collaboration of many universities funded by the government of São Paulo. Here's the University of Campinas, that's the University of São Paulo, and some others around the world, like Purdue, Notre Dame, Milano, Siena in Italy, University of Warsaw in Poland, and also Singapore. So here are some of the problems, and I'm going to give you some examples now. The first one is protect our children. So child pornography is a very important problem that we need to detect nowadays in terms of looking at the content. So if someone sends a video to another person, how can we automatically detect that that video is a video of child porn? A police officer, an expert, needs to watch that movie to see if it's child porn video. But when you have millions of possible videos shared online, it's impossible and gruesome. And of course, it's not something that you'd like to do. So our idea here is to automatically filter the content and spot for possible analysis later those kind of contents. This started as a research funded by Samsung. They wanted to create a detector of normal pornography and violence. So we were funded by them to create this filter. We created, it was like patented, and it's now present in the smart TVs of Samsung when you go to parental control. At least in Brazil, the algorithm that's running the parental control, we did it. But then Samsung allowed us to continue the research and to make it available to experts to extend it to detect child pornography. So the thing is, we wanted to detect pornography and violence for Samsung for parental control to not allow kids to watch this kind of content automatically when a parent goes to the parental control option in the TV, or to detect child pornography when we do analysis of apprehended materials. But this is a difficult problem because we have some cultural aspects, especially in Brazil. We have Indians, indigenous people. They have like their celebrations. And of course, when they have their celebrations, they are not wearing clothes. So this should not be tagged as pornography. The algorithm should learn that. Or if you have like a medical emergency and someone is like trying to resurrect a person with like some cardiac massage, this should not be tagged as violent behavior. This should be something that the algorithm learns. So this is the kind of complications that we have when we try to solve this problem. So we did this in partnership with Samsung and also the federal police because we could not directly deal with the data of child porn. So we needed to develop an algorithm that should be boxed and sent to the police. The police would run, then give back the parameters to us. We would adapt the parameters and we did this back and forth with them. And the algorithms were trained with hundreds of video hours of pornography, hundreds of video hours for violence. And our team needed to do this annotation, and it was quite complicated to get the authorization of the university to have like hundreds of hours of porn inside the university servers. But we needed to solve the problem. So we got the authorizations and we did it. So our solution has 3 levels. In the low level, we developed the detectors. The ones existing in the literature didn't apply to us because we needed to do detection fast enough to run in the TV and a cell phone. So we needed to extend these and also to work with videos. Then we needed to code that such that we could capture the properties in terms of semantics. And then in the high level, we did the classification. And we also needed to focus on the parts of the videos that had motion. So at the time, there was no fast enough detector. So we developed our own detector to work with videos. Here is an example of that. So if you have something moving, the detector goes and specifically marks the part that's moving. And then if we need to like run this over our algorithm, now we just focus on this region and discard the rest. So this started moving now, so it follows that until it stops. And we call this temporal robust features. And it's fast enough to run in a TV. So in the end, we needed to represent the images. So we do a 2-way network. One part of the network receives an image, which is a frame of a particular place that we selected the motion. So given the video, we select the motion, and then in that frame that has motion, we give it as input. We calculate the features. We do the same for the motion, calculate the features, combine the two, and in the end, you have something like that. And then as we analyze the video over time, we need also to detect over time. So we start looking at the sequence. So it comes 1, 2, 3, 4 frames. So we analyze the first snippet. Suppose that we are analyzing 3 frames per time. So 3 frames, get an answer. Then I move 1 frame, and then I get the next sequence of 3 frames, the next sequence of 3 frames. At some point, I'm going to have different answers for one particular frame. How can I combine the answers? So this was the motion aggregation that we proposed. It was published like 3 years ago in Information Fusion, how to combine different classifications over time. This applies to video, but any temporal series that you might have more than one classification per point in time would be interesting to use something like this, okay? So when you have something happening over time and you need a buffer to start, and after that buffer, each time that you receive, you might have more than one classification because things change. As you get more information about what's coming, you have more confidence of how to classify. So you start classifying the first frame, but then you are not so sure. You say that's class A, but then you go to the next frame, you have more confidence about the previous one that you classified. So perhaps that one now is class B. So when you have these different classifications over time for the same frame, for the same time point, how do you do? So this was what we proposed. In the end, we can detect pornography with 95%, violence with 85%, child pornography with 85%, and violence with 80%. Violence is by far the most difficult because you have many different levels of violence. And it was possible to detect with 80%. Some kinds of violence are easy to detect. For instance, fights, street fights. So when you have a football game, I don't know here in Greece, but in Brazil, football games are very fierce. So we have, it's very common to have like street fights on football games. So you have the CCTVs. How do you detect that quickly? So for that kind of thing, it's more than 90%. But if it's just an arguing between two people, it's more difficult to detect that's violent behavior. So in general, for the kinds of violence that we have, it's 80%. Okay. Oh, by the way, if you have questions, you do not need to wait until the end. Okay, just raise your hand and ask. And this is present in smart TVs, IoT devices, mobile phones, and then also freely available as a virtual machine to anyone interested in detecting child porn. And this was presented to Interpol, like this is 2019. This was 3 and something years ago. So another thing that we are doing is trying to understand the signals of mobile phones. Please go ahead.
So if you don't mind interrupting.
No.
Very, very interesting. I have a couple of questions. Should I ask them now?
Yeah, please go ahead.
Okay. So the first question is a bit of how did you manage to do the training without access to the data? Was it a federated learning solution, or was it an iterative process?
So it could be federated learning, but we didn't use federated learning here because the experts in the police, they didn't know how to do the part of federated learning. So the only thing that we could do was this. This is a three-layer learning. So the first layer, we needed to detect, we needed to learn image features in general. So we did with ImageNet. Okay, so we got something trained with ImageNet, any network that you want. So the second thing, we needed to tell the network how to learn what's pornography. So we trained it with like 150, 200 hours of pornography. So now the detector is good enough to detect pornography, but it doesn't know what is child pornography. So now we create a sandbox, sent to the federal police, and they have like 40 hours of annotated child pornography. They run the 40 hours over the algorithm, and they update the weights, send back to us, and then we analyze if the results are good or not, because they have also separated test set.
And this was frame level annotation?
Frame level annotation.
Okay.
And it has a lot of problems because my student that was doing the annotation, he is married, and sometimes his wife, oh, you were watching porn. No, this is for the good of science.
Okay, thank you very much. And a couple of other questions. The first one is in the image where you saw the processing pipeline, it implies that there are some people in detectors that use.
Yes.
So this was not based on the CNN, but based on people in detection.
This is pure vision, computer vision 101. This is what we call temporal robust features. If it was an image, we could use like surf, sifts, or something, right? But it's a video, and it needs to be fast. That's why we developed our own. It's an extended version of surf that works with videos.
And it's robust to motions of the camera.
Well, normally when you have pornography, you only have viewpoint change. You do not have camera change normally. So when someone shoots video porn, it's like camera can be here, there, but they do not change cameras normally. So it's robust to camera change, camera viewpoint change.
Thank you very much.
Okay.
Actually, it's not a question, it's more like a discussion about the child pornography case. This problem is global, and there is a European project involving also Europol, the European police, that deals with that. I wrote that proposal, it's now an ongoing project. What we decided together with Europol was to follow the federated learning approach, because the main problem there is that they didn't want to have any data outside of their premises. And we designed a framework with the central police of 4 or 5 European member states. Only these had access to data. And what we did, perhaps in the opposite direction that you did in your lab, only police officers had some access to interface for the annotation. No students, no academics, no professor, because here in Europe we have the GDPR, we are strict. But this project is ongoing. We want, I can put you in contact if you are still interested.
Okay.
I'm not participating right now. I just
That's good.
design the whole system,
That's good.
and you can always have a separate
Thank
data
you.
because it's exactly a problem I'm aware of.
Yeah, this is a very important problem. We never had access to child pornography cases. Only the police had access to that. We did the frame level annotation for the normal porn. Okay,
Exactly.
but federated learning extension would be very important. And if you can start the federated level with something learned, trained like this, it's already 85%. Now you can just update the weights and see what improves, right?
Well, in Grace project, the actual evaluation was not performed by the scientist. We only did set the loss function or
Yeah,
just to get
a feeling of its working.
How good is it, but never see the actual evaluation. How
Yep.
good is it in practice.
That's good.
Side comment, okay.
Thank you. Another thing that we wanted to identify is this. Suppose that you are walking around with a cell phone and someone comes and snaps your cell phone and goes away. So it would be nice if the cell phone could identify that you are not you. So we asked ourselves, is it possible to detect that my owner, suppose that you are the phone, my owner is not my owner anymore, based on the way that you walk. So you walk every day with your phone, either in your hands or in your pockets or in your purse, but the phone is with you. It has a lot of sensors. So you can analyze the trajectory. So if you can analyze the trajectory, you could learn the way that person walks. If someone snaps that phone and starts walking, the way this person walks is different. So I could automatically block the phone, and I would only unlock the phone if the person types the correct password. So this was the idea. And we call this user agnostic motion profiling. So what we want to do is something like this. We receive the signal. It can be accelerometer, magnetometer, gyroscope. We process the three. So we transform these signals in what we call input space transformation. So we represent the signals with hybrid images. So each signal is now an image, and it's very nice to use these different ways. We propose several different ways of transforming signals into images. And it's very nice because you can see the signal. I'm very bad at analyzing time series, but when I transform the time series into an image from John is going to be very different from an image from Mary, which is going to be very different from an image from Anderson. So I get a window of time, transform that into an image, and this image, this hybrid image, is the input of my algorithm, and the network that I designed works on top of these hybrid images. More than that, we don't work with just 3 channels, because a normal image is like R, G, and B. In our case here, we propose to work with more channels, like a tensor. In our case, it's 6. Why is that? Because we want to distinguish if the image of a specific time period is from the same user or a different user. So what do? I get the signals from one person, and accelerometer, gyroscope, magnetometer goes to the 3 channels. And then I get the other channel. The other 3 channels is going to be for someone that I compare to. It might be one element of another class. And then when I give to the network, I train the network same or different. If I give an example of one time period for John and another time period for John, this is the same person. So I train the network to be the same person. If it's a time period for Mary and a time period for John, then the network learns that these are from different people, different persons. So this is the idea. And what we also need to do this, pulling the decisions, because we have the detector over time. So we move 1 second each time. And we do this temporal coherence as well, because as time goes by, we are more confident about decisions. So this was published last year in the Pattern Recognition journal. And the idea is that you are able to separate the users. But when we projected the training and testing, there was a time, there was a domain shift here. So we needed something more. in terms of projection. So we also designed the projection to force the samples to be close together when they are from the same class and far from each other when they are from different classes. So here is one of the examples of the domain shift. The training data is here, the test is here, so this is domain shift. Ideally, they should be overlapping. So to be able to understand better these trajectories, we partnered with McGill University, and we wanted to evaluate if the accelerometer was good enough to analyze the way people walk. To do that, we needed to buy like the best accelerometer possible. That's the IMCU here. So it's like a complete unit for accelerometer analysis. And we put this on the P here. And we put a lot of other accelerometers as well in the person to see if we can capture the way the person walks. Of course, in production later, we are not going to have this. We are only going to have this accelerometer of the cell phone. But what happens if I analyze all of this? Do they compare to just one accelerometer in the cell phone? This was the question. And for each of those, we capture like the time series. And we move the time series 75% each time, keeping overlap of 75. So here's an example of the trajectories of each of the sensors. You can see that they capture different things. So we need to put them together. Here's the transformation that we propose. That's called the user coordinate acceleration. So independent of the position that you put your sensor, we transform everything to be like in this position. So when you have the cell phone, it has its own coordinate system. So if you put the phone here this way or this way or this way, it's going to be in a different position because it has its own coordination system. And we have ours, which is the word coordinate system. So we transform this coordinate system to a user coordinate system, always with the phone pointing up in this position. So independently of if you put the phone here or here, it doesn't matter. We always put here. But it's not perfect. It still has some approximation problems. But when you do that, you can guarantee that the training and testing of the same person is different from the training and testing from the different persons. So now you have a separation between the two classes. Now I could separate a person because when someone comes here, when I get the phone the first time, I registered myself. So the phone asks me, walk 5 minutes. So I walk and it learns, it creates this sampling of myself, it learns the features of my walk and done. This is registered here. Now, if any other person tries to use my phone, it will capture like 5 seconds of that walk and compare to what's registered here, it will answer. Same user, different user. As times go by, same user, different user, all times. Okay, so this is the idea. So it's a two-class problem. If I'm myself, I get my phone, I start walking, the phone knows that's me because over time it gets the data, compares to what's stored here. It's Anderson, it's Anderson, it's Anderson. And as it confirms, it can learn more. It can save that data. So the 5 minutes that started when I registered now can be 10, 15, 20. I can define maximum of 2 hours, and then I can get rid of the old data. So I can adapt over time. So this is what we do. And whenever I need to do a test is the new data that I just captured is from the same user. Yes, keep using the phone. Yes, keep using the phone. Yes, keep using the phone. And this happens under the hood. You don't know. You do not need to know. It's not like you type a password. No, you are using and it's doing the analysis. And it only does the analysis when you are walking. So the phone also has a classifier that knows if you are walking or doing anything else. So this walking classifier is 99% accurate. So you start walking, it knows 99% you are walking. And then once it knows that you are walking, it tries to authenticate you under the hood, transparently. Okay? All right, so this is what we did for this problem. It was funded by LG, the South Korean company, competitor of Samsung. And it was recently published in I think 2 months ago in Nature Scientific Reports. If you're curious about, I can share the reference later. All right, how are we in terms of time?
That's good.
It's okay. If you have more questions regarding this, please go ahead. No questions? Okay. So this is another research that we have been doing. It's about fake news detection. Since day one of the pandemic, we partnered with Carnegie Mellon, and the idea was we wanted to collect everything possible that appeared on social media mentioning COVID-19, SARS-CoV-2 in English, Portuguese, Italian, the Western languages. Okay. We collected every day, and now we have about 1 trillion messages saved. And we are now exploring this data to see the patterns. And we already can see some patterns. For instance, you know that Brazilian president is Bolsonaro and the US president was Trump, and they were very much aligned. So anything that Trump said 8 hours later would be translated in Portuguese, and it would be in Portuguese around the networks in Brazil, and vice versa. So Bolsonaro said, Trump said something about chloroquine that's good for COVID-19. So 8 hours later, that piece of news would be translated in Portuguese, and everyone would be sharing that over WhatsApp. Then Bolsonaro did his contribution. Ivermectin, have you heard of ivermectin? Ivermectin is very good for COVID. Ivermectin is a worm fighter. A person takes that for worms, but normally is for pigs and horses to fatten faster. So Bolsonaro said that it would be good for COVID-19, and then 8 hours later, it was translated in English into English, and people were sharing that in US. So we can see some of those patterns happening based on this data, and it's interesting to see, but it's sad that we had also, in addition to the pandemic, we have also the infodemic, the pandemics of fake news. And here, what we would like to do is to help fact checkers to identify fake news, but differently from other groups that try to classify a piece of news as fake or not. We, talking to several journalists, we figured out it would be very difficult. If we are not Facebook or Google or something very big, if we don't have that amount of data, we could not do that. So we asked them what could be useful for them to help them in a daily basis of checking the news, if they are real or fake. And they said that the most important thing for them is fact checking. So when they receive a piece of news, to check if it's real or not, they do what's called fact checking. They decompose the text into the facts, and for each of the facts, they need to check if this fact is really fact or not. 20, 30 years ago, when you mentioned, at least in Portuguese, the word fact, by default, it is a fact. So it's something that really happened, it's real. But with the fake news era, the post-truth era, a fact might be fake. So now fact checking is basically when you have a text to decompose, suppose that the text decomposed is like 10 claims. So for each of the claims, the journalist needs to check with different sources if it's real or not. And then at the end, if everything adds up being true, then the piece of news is tagged as not fake. At least there is no evidence that's fake. This is what they do. So this is what we wanted to do to help them. So we started naive. We started thinking, okay, let's try to do a classifier for fake news. And I'm sure that every researcher and student sometimes think naively about the problem and think that AI can solve the world, right? We did this, we published this, but in the end, it worked only for the data set that it was available. We could beat the state of the art, but it worked only for the data set. And when we gave it to the journalist said, yeah, this is correct. It doesn't work in reality. So that's when we shifted gears and we started working with the fact checking. But what we did here, and this might be helpful in the next stages, when you receive a piece of news, we also collect from the internet the comments about that piece of news and also the social media messages about that piece of news. So the three of them go to the network, and then we convert this to a vector representation. This is like a transformer, okay? So it goes like this, it transforms this into vector, vector. The three of them are projected in this 761. And then from here, we go until the end with a yes or no answer. Why did the journalists say that it was not useful? Because when you have a piece of news, and when you come, the idea would be, if people here say in the comments, oh, this is fake, this is fake, this is fake, or the comments, this is fake, this is fake, the network would see that something was wrong. But the problem is people live in bubbles. So again, our scenario is Brazil. So when a piece of news comes and some people start saying that's fake, of course, the supporters of the other side will say, no, that's not fake. This is true. I know my uncle did this. My mother did that. So chloroquine helps COVID-19. Some people here, no, it doesn't. It's fake. There is no evidence that it helps. Then a Bolsonaro supporter comes, no, it helps. An aunt of mine took it and was good in 3 days. Oh, my friend took it and it was good in 2 days. So you have mixed comments about the news. So how the network can detect that kind of thing? It doesn't. So the comments and the social media should be used to refute the message. If the humans were good enough to spot it, the network would spot it. So it doesn't happen. So that's when the journalist said, no, what you actually need is to decompose it and to help us answer the questions. So now what we do, this is the normal process of fact checking that we talked to the journalists. They decompose, choose one claim. This claim is assigned to a team. This team does the research. And then this research can turn up to be like fake or not. So then they write the report, edit with skepticism, and publish it. So this is what happens normally, but you can see that's very time consuming. So what we would like to do is to help them in the process of decomposing, in the processing of checking the claim, so that we could rank some of the things for them so that they can quickly or in a faster way detect that something is wrong. And we do this using explainable fact checking. This is something that we just published this year in ICASP. And it's surprising because ICASP is a conference of signal processing. And we are doing language processing. But why we do that and why did we get accepted there? Because we transform text into signals. And for us, everything is a signal, and we do everything with convolutions and everything like we are used to in our lab. So that's why we were able to do something here. We are not experts in natural language processing per se, but we are experts in signal processing, in machine learning. So what we do is this. We get a text, suppose that's something like this. Lee MacPhail passed away, and this is like a standard data set in the literature, okay? Lee MacPhail passed away at his home at the age of 92. So we create a transformer to receive passages, decompose those passages into questions. So for instance, something like this would be transformed. How old was MacPhail when he died? Where did MacPhail die? So once we do the question, we also train the transformer to answer that question. So answer for the claim, 92. at his home. And then we do this for the entire piece of text. So this is done for the claim. Then based on those questions, we go to the internet, in our case, Wikipedia, and get evidence, if we can. So the evidence coming from for instance, from Wikipedia. MacPhail lived in Delray Beach, Florida, where he died November 8, 2012 at his home. He was 95. At time of his death, he was the oldest living Hall of Famer. Okay, now we decompose this into questions and also answer those questions. Now we compare the answers. See, 92, 95. Then we found an inconsistency. And for all of the inconsistencies that we find, we rank them and give the importance based on the XAR. So this one and this one should be something that we should look at more carefully. We rank this and show to journalists, and then they have something to help them. So this is what we are doing now. Of course, it's just the beginning. It's just a conference paper, but we already discovered that it has potential, but a lot of problems, like many of the questions are similar. So we need to improve the quality of the question generation. Some are even repeated. But at least one interesting thing, the answers normally are correct.
Can I ask something about this? You mentioned that you generate the questions and answers using transformers, transformer networks.
Yeah.
And and then you have an extra layer of transformers and use the attention weights from that to indicate the compatibility. Okay. And is there any convolution used in this pipeline?
Transformers is all convolutions, basically. Well, depending on the architecture that we use. In our case, the transformer that we use is simpler. It's BERT. Have you heard of BERT? Yeah. So it does not use the convolutions the way that we know. And the explanation part is done with line, L-I-N-E. Okay. So it's just one module coupled with the transformer. And in this case, the representation for this particular paper was just transformers, no convolutions. But we also have a paper that we do the same without transformers and just with convolutions in the signals. In that case, we did the architecture, but it was like a CNN. Okay. More questions?
It's a less technical question, but how do you deal with like the tone of the text or irony within the text, and how are you going to make the algorithm detect like irony or metaphors?
That's a very difficult question. I don't think that we have in the data sets available right now some annotation for irony and those kind of things. And this is what makes us human, right? Detecting irony is very, very difficult. I would say that even if you train a specific detector for irony, I'm not very confident that the result is going to be very good. But right now, we don't have any kind of irony detection.
But I would assume that in this kind of statements, where one wants to, spread out fake news or something like that, they wouldn't be using irony.
No.
Most likely, they would be using some kind of authority.
Most likely, they use authority, like they want to be strong.
Yes.
Show a strong opinion about something. So they are very, very clear about what they're showing. They're very fierce defenders of that idea. So there is no irony. Oh, because I used to joke with my students, irony is something of the smart people, right? So far right people, they are not that smart. Other questions? So here is another one, and this is also quite worrisome. There are some studies that show that 5 to 10%, at least 5 to 10% of publications in science have forgeries. So here we decided to focus on only biomedical research, biology and medicine. and to detect forgeries based on the images, not the content. So if the person fakes the text, we would not get it. But if the person edits the images, we would get it. Okay? So what we want to do here is something like this. So this is a result of a paper, and this person got this result and changed colors and rotated the image to show that perhaps this is like coming from a different sensor or different capture position. So this is the same result, this is the same result, this is the same result. And it goes in different papers. So how can you detect that? Or something like this. The person here got one good result. I'm not an expert in biology, but according to the paper of this image, if this result was present in more than one place, this result would be considered as a whole a good result. So this person goes to Photoshop and replicate it. So like cloning. And here, and here, and here, this is present in many, many kinds of images. This is just one example. And another thing that they wanted to do is they found recently, about 3 years ago, one thing that's called paper mills. Have you heard of paper mills? Paper mills is like a fabric. It's like an industry of creating papers. So these authors, they get united. They like 10, 20 authors, they start citing each other to boost citations. This is one thing, and we could not detect this. But they start reusing images of previous papers of other authors in their papers to claim results that they don't have. One example is of a very famous researcher of South Korea. He was a highly ranked researcher. Now he is dismissed. He claimed to have 11 cases of cloning animals, and he published it in Science. But someone looked at the results and was not quite convinced about the results and asked for an investigation. And after 1 or 2 years of investigation, they discovered that just 2 cases were successful. The other 9 were cases of cloning, but Photoshop cloning, not the biological cloning. So after this investigation, this guy was dismissed, and he's not a professor of this university anymore. But we would like to detect this kind of things. We would like to detect the paper forms. So how can we detect that? We have 2 levels. The first is we analyze the paper and we see if there is any signs of forgery in the images in that paper. So we receive the PDF, we extract the images, we analyze the images. If they're okay, done. If we find some kind of evidence that something might be wrong, we get all of the author names, go to Google Scholar of each of the author names, get all of the PDFs available for all of the authors, extract the images of all of the PDFs, and compare the images to see if any piece was reused. Okay, this is what we call provenance. Provenance is like the study of the origin, the acquisition process, the creation process of something. So this would be like the pipeline. We received the paper. We did this analysis in partnership with Retraction Watch. Probably you have heard of it. It's a website service. I think they are based in Europe. They keep track of retracted papers in many journals. So we got, in partnership with them, we got their data sets, their database. We analyzed all the retracted cases. And then we proposed the algorithm to extract this. And then we decompose each box of this in the pieces, because we cannot analyze the box itself. Otherwise, we would think that one bar plot was copied, but it's just a bar plot. So we separate the panels, we classify the panels, the ones of interest we separate. And then we go compare to the click of all of the authors, and we see if there is any evidence of reuse. And if there is, we can also link the authors reusing the content of each other. So we know that John is reusing the content of Mary and things go down from that position if Mary also reuses the content of another person. So in the end, we create what we called Provenance Graph. This paper is just accepted. It's in partnership with DARPA, the Defense Army of the US. They funded this research, and we did with Purdue and Notre Dame. The idea was to do this as a freely available to publishers like Elsevier, IEEE, and the Nature Group. It's not available to the general public yet. The paper is accepted in Nature Scientific Reports and should be out in about 2 or 3 weeks. The problem is that this paper is it has been accepted 3 months ago, and we are discussing with the editors the cases that we detected, because it's like they are afraid of being sued because we detected some forgeries. And they said that we cannot point out the names. Then we said, okay, we are okay not citing the names, but we would like to show the images that they forged. And no, but they are going to discover that but they fake it. So we are kind of discussing with the editors what to do, but it should be out soon. So I think that we are out of time, right?
Yeah.
So I can answer some questions if you have.
I have a general question, but maybe it's better to leave it at the end. In general, for instance, for this one, it's a kind of big system created.
Mm-hmm.
So my question would be, in terms of effort, what's the balance? How much time do you spend in actually building the system and doing the modeling?
No, in my case, my team was involved in the AI part. So if you think of this pipeline, we were more doing this part, and this part. The part of transforming this into a software, it was the USC, University of Southern California.
Mm-hmm.
So transforming each of the modules that we developed in Python into something for another person to use, it was them. So I don't know the amount of effort they put to transform this into a system, because as researchers, we only do the modules, right? The MVP, and if you change computer, it might break, right? But in this case, they defined the inputs, the outputs, so we did the module, it gave to them, and they integrated. But I know that it was quite a few hours they used in this. In the case of the child porn and the detector of general pornography, we did everything. We had the programmer in the team. It was a team of 1 PhD student, 1 postdoc, 1 master student, and 1 programmer. And everything was the result in 3 years. So the result that showed the detector was ready as the 4th of 3 researchers, the master, the PhD, and the postdoc in 3 years. And then the programmer followed all the time. So the programmer was with these 3 all the time. So whenever something worked, the programmer already started coding that for the TV and the smartphone. So we always need to have, if you are with the industry, if you really want to have something for them to use, you need to have a programmer, because in the beginning, we thought that the students could do it, but then the student was more focused on trying to solve software engineering problems than the scientific problems. So that's why now we try, whenever they want the code, we try to have an engineer to implement the code.
Thank you for, I just wanted to say that it was a very interesting, very nice presentation. The work that you're doing is excellent. And I have a follow-up question. And it has to do on what is the process with which you collaborate with the industry. So do you usually go to them with your ideas and we start discussion that, or they come to you with the problem?
Right. It's both ways. Yeah. It's both ways. Normally, you need to to be in a university that already has this tradition of being open to the industry, right? We have in Brazil some universities that don't have this tradition, so they are not even looking for. So our university, it's open to this kind of partnership, and that's why we have one fast track of contracts. So if an industry decides to do a partnership with us, it's like in 2 months we have the contract signed, and it's like compared to the old Brazilian bureaucracy, this is like light years, so it's very fast. So sometimes they come and they say, oh, we have this problem, but then you need to create the project because they have the high level idea. Oh, let's talk about one that's very fun, easy, but fun. An agro company came to me some months ago and said, oh, we have this problem. We have a production of about 30,000 eggs per day. And we needed something to count the eggs automatically, because right now there is a person there counting the eggs. And okay, we can do that. It's pretty much, it's computer vision, right? So we put a tripod with a cell phone, so like Samsung S8 or a Galaxy or something, put a cell phone on top of a tripod and you film the eggs coming on pellets. And then we could count with like 100 more or 100 less. But then the person said, that's awesome, because 100 more or 100 less, even a person would get it wrong because it's 30,000 eggs a day, right? So that's something that they came to us to ask for a solution. And this was not even like a project. This was like a consulting. I put a PhD student of mine, the PhD did the consultancy. He was happy, got the money, and put in his curriculum that he did the consultants for an agribusiness. So sometimes it happens this way. Other times we have these presentations, something that like the thing that I presented to you today, we have this portfolio of presentations. And we go to companies and we show them, okay, we work on this. So if you have a problem in AI or machine learning that you need a solution, look for us. And then even though they are not working with the things that you presented, you can see applications. So this is this also happens.
Thank you for your presentation. You mentioned that you made the classifier for child pornography to be able to work on IoT devices, smartphones, TV.
The child pornography, no. What worked with the IoT devices, the TV and the smartphone was the normal pornography detector, because this was the interest of Samsung. For the child pornography one is like a virtual machine that works on a desktop.
Nevertheless, how did you manage to make the network lightweight enough to be able to work on a Samsung TV?
That's a good question. We transformed all of the convolutions, like the mobile nets. Have you seen mobile nets network? It transforms the 3x3 or the 5x5 convolution into simpler ones of 1x1. So we transformed the convolutions into 1x1s, and we also simplified the floating points, so like to become integers. And doing that, our network ended up being, I think, 38 megabytes. But now, well, that for the time it was a very good size, but then someone else did like 5 or 6 megabytes. So there are networks of 5 or 6 megabytes now. Ours was about 38, 40. It started with 500. Thank you.
Just to get it straight, is there something else that you would like to
I had, but we can't finish here. It's not a problem. It's up to you.
If there's one more topic, I guess.
Okay.
Really short.
So 5 minutes about this one. Here is a topic that I was talking to Konstantinos earlier. Many times we receive a problem for which we don't have labels. So here we wanted to solve a problem in a way that we automatically find the labels and we propose labels, and the machine will adapt over time. Okay, So we started this problem with person re-identification. The idea is that why we did that, because this is like the perfect scenario for learning different labels, because it has changes in viewpoint, pose, illumination, occlusion, background, and everything. So it's a very difficult problem. Two images of the same person will be likely more different than an image of this person and another person wearing the same clothes, for instance. So this is why we started with this. We have no identity annotation and no other side information. And when I say side information here, is because sometimes I can use the information of the camera that captured the image to help me in the clustering. But here I have no side information. Everything that I receive is like a box of a person, a pedestrian detector. And up to this point, any detector could be used, YOLO or something. You just give me the region of interest, the ROI, and then I work with this, okay? So the idea is we work with, we propose a pipeline. It's a self-supervised learning pipeline. You receive the different images, and then we have the feature extraction modules. These might be one network, this might be another, this might be another. The number here is not important. We work with three, okay? 3 standard networks trained with objects, right? CNNs. Then for each one of them, we create a matrix of distances. For instance, suppose that we have 10 images here. So if you have 10 images, each of the 10 go to these 3 networks. So here I can create a matrix of 10 by 10, 10 by 10, 10 by 10. So I know the distance from anyone to anyone. And then in the end, I combine these distances and I have this visualization. Okay, this is the first step. The first thing is, normally when you do this here, people try to do, for instance, max pooling or average pooling only when combining distances. We discovered that when you have a scenario of no labels and many differences between the classes and intra-classes, it's better to keep the 2, the max and the average pooling. So we have the 2 distances matrix here. And when we do the clustering, we also discover that instead of forcing a point to be part of a label, it's better to say that you don't know. If you're not sure enough about a point, it's better to say I'm not sure. So here, when we try to cluster, we are going to propose labels. For instance, here I propose the label orange, this yellow, this dark yellow, this gray. If I'm not sure about a point, I say that's black. So at this iteration, I'm not sure if that point is of the same class, so I put it black. Here, I put it black. Then in the next iteration, with a different parameter of the clustering, I might revisit this and I might say that some of these blacks are actually part of the orange. Or I might discover that some of the blacks are indeed another cluster. So I do this with different parameters for the clustering. And this is not k-means, because I don't know the number of identities. I don't know the number of classes. So there is no k that I know. So we do this with DB scan, for instance, and with DB scan, I can analyze the density of the clusters. But of course, I don't know what's the perfect density, so I do with different densities and combine them. Oops. And then we also put an explanation module to understand the results. So for instance, I want to detect this person. So all of these images were retrieved. And what's important about that particular person? Oh, the bag here, the shoes, blue here, a little bit of the head, but not so much because it's not red, and the backpack. So you can see that's consistent across the different images. So this is a correct case. One interesting case, when the algorithm fails, it tends to activate pretty much everything in the image. So it tends not to focus on a particular place, but spread the attention. So we can now extend our method to a post-processed result and analyze only the map, the heat map of results, of the understanding of the result. And then a simple classifier could say if it's something like this or something like that, but we don't have this module yet. Right now, we have this that combines the different distances, that does several rounds of clustering with different parameters and combine all of them. Another novelty of this method here is that how do I decide if this point is part of this cluster? How do I decide if a particular point is part of a cluster? Everyone, when tries to do clustering, they look exactly only at that iteration. We look at all of the iterations before. So if a point was black at some point, I keep track of that. So it was not now, not now, not now. Now it's a point that I know of. So I keep track of all of the states of a point had in the past. So this might be useful for me to decide now if it's going to be something that I'm going to say that's a noun class or it's still a noun. Another thing is to decide if a point belongs to this particular cluster. I look at his neighbors. But I look at his neighbors not only at this iteration, I look out also at his neighbors in the previous iterations. So the neighbors of neighbors now, over time, give me more confidence about including this point or not as part of this cluster. This is the main novelty. So looking at the temporal neighborhood and also at the neighborhood physical neighborhood in the cluster. So I think that this is pretty much it. To conclude, you might have observed that all the algorithms that I presented, we tried to come up with some explanation because this allows us to understand a little bit more of the decision. So we are trying to open the Pandora box of machine learning. So it's not just a yes or no. We try to understand the results. It's not there yet, but we are trying to do that. And this was what I wanted to say. Thank you.
Thank you. I assume that if there's any other question we have here, people can come and grab you.
Yeah. You can write me an email or LinkedIn, or you choose it.
Then.
I don't know if someone from the people watching online this presentation would like to ask something, then you should. All right, then I assume that thank you very much.
Thank you.
So it was really interesting. And we hope to see you soon in Brazil, perhaps.
Oh yeah. As I said, we are open to visiting students and also for open for collaborations.
Thank you very much.
Thank you. Can you take a picture of me in front of this?
Sure.
I need to